Assalamu alaikum everyone. My name is Umair Abbas Siddiqui from Dera Ghazi Khan. I am presenting today a research on Bug Hunter's vulnerability report. I've examined the complex landscape of software supply chain security, focusing on how standardized frameworks help categorize and mitigate digital threats. Central to this is CWE 420, a vulnerability where an unprotected alternate channel allows attackers to bypass primary security controls, as seen in real-world instances like CVE 2025-67338-3. Vulnerability databases and intelligence dossiers track these risks across major ecosystems, including Go, NPM, and Python, highlighting prevalent issues like path traversal and SSRF. To manage the sheer volume of daily discoveries, the industry utilizes automated mitigation loops that cross-reference software identities with global threat registries. This unified taxonomy enables security teams to trace a high-level threat down to a single line of exploitable code, facilitating rapid remediation. Ultimately, my advocacy is all for a transition from manual auditing to an autonomous immune system for global software infrastructure. The digital world faces a massive crisis because thousands of security flaws emerge every day across various technological layers, creating an unmanageable state of disorder. To combat this, the proposed strategy involves implementing a globally unified taxonomy that provides a standardized language for identifying these risks. The ultimate aim is to meticulously map the anatomy of a threat, moving from broad international classifications down to a single line of exploitable code. By achieving this level of precision, the system can deploy an automated mitigation loop that effectively secures the entire software ecosystem. Furthermore, outlines the current topography of the active threat landscape by categorizing specific security vulnerabilities across three major programming environments: Go, NPM, and Python. By analyzing over 4,000 advisories, the report identifies that SSRF, prototype pollution, and path traversal remain the most prevalent methods used to compromise the modern application layer. These weaknesses are particularly concerning because they are seamlessly inherited by modern infrastructure, including AI services and container systems. Ultimately, I aim to highlight how persistent software flaws continue to pose significant high and moderate risks to the foundations of global digital technology. The circular framework, known as the Mitigation Universal Automated Loop, which transforms cybersecurity from a manual chore into a self-sustaining autonomous immune system. The process begins by using universal, standardized metadata to establish a precise software identity, which is then cross-referenced against global databases to identify active threat intelligence. Once risks are identified, the system performs triage and remediation by weighing the severity of a flaw against its specific environment to launch immediate fixes. Ultimately, this integration of universal standardized data allows the industry to secure the software supply chain through a continuous machine-led cycle of detection and repair. A collaborative lifecycle of a cybersecurity threat record, which begins when authoritative bodies establish a foundational report detailing a specific vulnerability and its impacted software. To make this information more actionable for security teams, secondary contributors provide data enrichment by layering additional insights onto the original entry without compromising its integrity. These supplementary details typically include standardized severity ratings and root cause analyses that help organizations prioritize their response efforts. Ultimately, my framework demonstrates how a simple notification is transformed into a comprehensive intelligence asset through the systematic integration of operational context. Moreover, universal standardized terminology used by cybersecurity professionals to categorize and respond to digital threats. It organizes complex industry acronyms into four logical categories that define the nature of a flaw, its underlying cause, the level of danger it poses, and the specific location of the affected technology. By distinguishing between individual security bugs and broader structural weaknesses, the framework provides a comprehensive toolkit for measuring risk and prioritizing repairs. Ultimately, this chart serves as a foundational guide for mapping the life cycle of a vulnerability from its discovery to its remediation within a network. A systematic approach to monitoring security weaknesses as software evolves through different iterations. By categorizing releases into affected, unaffected, or unknown states, the model provides a clear visual timeline of when a system is at risk versus when it is secure. A distinction is made between linear history, which shows continuous development, and snapshot history, which captures isolated versions. This serves as a guide for automated patching, requiring users to properly organize version data to ensure vulnerabilities are effectively remediated. Critical cybersecurity flaw, where protective filters are only applied to a system's most visible entry points. While designers focus on securing the main interface with robust authentication, they often leave alternative pathways, such as hidden sockets or direct hardware links, completely unguarded. Attackers exploit this oversight by navigating through these secondary channels to reach sensitive data, effectively performing an end run around the allow list. By bypassing the primary gateway, these malicious actors can interact with the protected asset without ever triggering the security protocols intended to stop them. Critical hardware security vulnerability, where a protected system component can be compromised through an overlooked duplicate. The original design contains a flaw because the authorization check only monitors a single primary register, failing to account for a mirror or shadow register that contains the same data. By targeting this secondary address, an attacker can bypass security protocols and modify restricted assets without detection. To resolve this, the hardware code must be updated to ensure that validation logic explicitly covers every possible entry point to the secure data. I've technically specified by outlining specific cybersecurity weakness where a system heavily fortifies its main entry point but leaves secondary pathways unguarded. Often rooted in the initial architecture and design phase, this oversight occurs when developers fail to implement consistent security measures across every possible communication route. Because this flaw is language independent, it poses a universal threat to both software and hardware environments by undermining basic access controls. Ultimately, the presence of these unprotected alternate channels allows attackers to circumvent standard defenses and escalate their privileges within a network.